the institute was that he would have the privilege of walking back home with Gödel in the evening. So in other words, Einstein thought that Gödel was the smart one. Okay, so his most important contribution was his two incompleteness theorems: the first incompleteness theorem and the second incompleteness theorem. And what is this about? It's really about inherent limitations of mathematical reasoning, way of producing mathematical theorems, the way we do it. So to set the stage, how do we actually do mathematics? We know that we discussed that, say, physics is based on mathematics, and you could say chemistry is based on physics, biology based on chemistry. Okay, so it comes to mathematics. What is mathematics based on? Mm-hmm. Well, mathematics is based on axioms. So any field of mathematics can be presented as what is called the formal system. And at the core of the formal system is a system of axioms or postulates. These are the statements which are taken for granted.
Given without proof.
Without proof. An example would be, so that one of the very first formal systems was Euclidean geometry, developed by Euclid in his famous book, Elements, about 2,200 years ago. And it's a subject familiar from school, because we study it. But what it's really about is about the geometry of the plane. And the plane, by plane, I mean just this tabletop extended to infinity in all directions, kind of a perfect plane, a perfectly even table. And so Euclidean geometry is about various geometric figures on the plane, specifically lines, triangles, circles, things like that. So what's an example of an axiom? An example of an axiom is that if you have 2 points, which are distinct, 2 points on the plane, then there is a unique line which passes through them. Now, it kind of sounds reasonable, but this is an example of an axiom. In mathematics, you have to have a seed, so to speak. You have to start with something, and you have to choose certain postulates or statements which you simply take for granted, which do not require proof. Usually, they are ones which kind of intuitively clear to you, but in any case, you cannot have any mathematics without choosing those axioms.
And you refer to those as the observer because they're kind of subjective.
The observer comes in the process of choosing the axioms. Who chooses the axioms?
The turtles that it's all sitting on top of.
As Alan Watts, like to say, who is watching the watchers?
Yeah.
And so in mathematics, but you see, mathematicians are so clever. It's really kind of like a game of mirrors.
Yes.
We often like to say, and I used to say that mathematics is objective. It's really the only objective science.
Yeah.
But that's because we hide this this fact
in the basement
actually is based on axioms, and the fact that there is no unique choice, that there are many choices. And so Euclidean geometry is actually a good illustration of this, because Euclid had 5 axioms. 4 of them were kind of obvious, like the one I just mentioned. And the 5th, which came to be known famously as the 5th postulate, was that if you have a line and you have a point outside of this line, there is a unique line passing through that point, which is parallel to the first line, meaning that doesn't intersect it. And Euclid himself was uncomfortable about this because he felt that it was kind of he takes for granted something that is not obvious. And for many centuries after that, mathematicians were trying to derive this axiom from other axioms, which were more obvious in some sense, and they failed. And it was only almost 2,000 years later that mathematicians realized that not only you cannot derive, but you can actually replace it with its opposite. And you will still get a bona fide, consistent, not self-contradictory, which is called non-Euclidean geometry, which of course sounds very complicated, but it's not. Think of a sphere, just the surface of a basketball, or the surface of the earth, idealized. The analogs, so you have points, you have analogs of lines, which are meridians, right? Every two meridians intersect, unlike parallel lines on a flat space. There is also so-called hyperbolic plane, where the infinitely many lines which do not intersect. So every possibility can be realized. There are different flavors. This is a good illustration of what a formal system is. You start with a set of axioms, those statements you take for granted, and this is where you have a choice. And by making different choices, you actually create different mathematics. After that, there are rules of inference, logical rules, such as if A is true and A implies B, then B is true. Most of them were actually introduced already by Aristotle, even before Euclid. And then it runs as follows. You have the axioms, which are accepted as true statements. Then you have a way to produce new statements by using the rules of logical inference from the axioms. Every statement you obtain, you call a theorem, and you kind of add it to the collection of true statements. And then the question is, how far can you go? How many statements can you prove this way? Of course, you want it to be the system to be non-trivial in the sense that you don't prove everything. Because if you prove everything, it would mean that it's self-contradictory, that you prove a statement A and its negation. So that's kind of useless. It has to be discriminating enough so that it doesn't prove contradictory statements. So that there is already a question of that mathematicians call consistency. It has to be consistent in the sense that it is not self-contradictory. And then the idea that was basically prevalent in the world of mathematics by the beginning of the 20th century was that in principle, all of mathematics could be derived this way. We just have to find the correct system of axioms, and then everything you ever need would be could be produced by this procedure, which is really algorithmic procedure, which actually could be run on a computer. Now, think about it. What is special about this process? In this process, you are just manipulating symbols, basically. You're going from one statement to another without really understanding the meaning of it. So it's an ideal playground for a computer program. It's a purely syntactic process where there are some rules, some rigid rules of passing from one statement to the next. Most mathematicians believed that this way you can produce all true statements. And if this were true, it would give a lot of credibility to the thesis that everything in life is computational, or life is computation. Because then, at least mathematics is computational, because then it can be programmed. And a computer, after sufficient time, depending on its capacity, would produce every true statement. So Gödel's first